Hi guys, my name's Matt. I'm a geologist for SRK, an environmental engineering consultancy based in Bristol. Now the old adage goes that the best geologists have seen the most rocks, but I think we should add a stipulation onto that they should also be a bit of a jack of all trades. When you get into the field, you're often asked to do a bit extra. You're often asked by our clients to do something that you might not have done before, or you're asked to specialise in something that you have no specialisation in. Now as a consultancy, we always say yes, and then kind of figure it out later. This project came to us about last year after we'd done a ground investigation for a residential developer. We had done the ground investigation and we found contamination. We had designed their foundations and we thought that would be it. However, when it came to it, we found that there would be a bit of a problem that the client came to us. The client's discharge of planning had to say, the highlighted bit at the bottom here, that all of the sustainable drainage should be complete for the relevant phase before anyone is allowed to occupy any of the buildings. So if we go back to here, we've got a road on here on Google that hasn't had the appropriate satellite image done. So we have phase 1 done already. We've got Charmouth mudstone in a basin, and there's no river or surface waters for any drainage to go. So, a bit of a problem. The client came to us and said, we need to work out what to do with the water if there's going to be a storm. Our client's got 71 hectares of development land, and as you can see to the south, it's quite highly densely populated already, and the areas around it earmarked for development as well. So, the planning officer had decided that to have a sustainable long-term solution for the drainage, that we had to come up with a solution to deal with the contaminated land we had found there originally and put in some kind of stormwater attenuation so that when the storms do come and that the infiltration drainage systems that usually were relied on fail because we built on them all, that all the tarmac and all the houses is going to discharge somewhere, but it has to go somewhere and they've already built on it. So that was the problem, and that was put to us by our client. We came up with a solution that hopefully killed 3 birds with 1 stone to deal with the contamination, to deal with sustainable drainage, and to save the client loads of money, because that's ultimately what they like. We came up with a plan to build a Boomerang Bund, so that's on the top left there. And this bund was going to be used as a stormwater attenuation pond. So when water came from the development to the south and from the areas to the east, it wouldn't discharge straight into the small kind of ditch network that it had been relying on so far. It would be held in this stormwater attenuation bund up here, and then it would have a throttled discharge from the head wall into the areas where it was allowed to discharge safely. So rather than flooding all the nice new houses in the Cotswolds and having some irate neighbours from the Cheltenham region, this was decided to be the best route. Now, we knew the geology of the site from the ground investigation, but we knew it was a bit of a double-edged sword because we had sands and gravels in the east of the site, we had Charmouth mudstone in the west, and we had contaminated land stockpiled from a topsoil strip. So this was our kind of procedure to go about it. We had to prove the resource. Now, we saw resources before of interesting things like copper and gold, but this is a more British resource in the fact that it's clay. A little less glamorous, but we had to prove it anyway, so we had to go there and do holes and work out our resource for what we could actually build from. So this area was a borrow pit that we designed. From the trial pitting and the boreholes that we put in, we worked out that there's only a kind of a small horizon of appropriate materials. So we had to do geotech testing on that Charmouth mudstone to work out if the properties of the clay were going to be adequate for building this bund. We did that, and we came up with a plan to build this bund, do it in layers, and do it in accordance with a few engineering documents from Syria, which are the pretty much gold standard for works of this nature. We looked at the drainage that was already there. We knew this was in August and there was water actively coming into the site. Something had to be dealt with it. We had some water already there. This is pre-development, and so we knew that we kind of had to act fast before all the kind of fast-track development in this area was going to go. And then this is a photo from one of the trial pits where we can see a bit of rainwater being held nicely in the bottom, got a good impermeable clay. And we've got a little topsoil horizon there, subsoil, and then we're straight into the Charmouth mudstone. So we could model quite accurately how much mudstone we had from the borrow pit, how much we had to put into the bund. The execution was about a 4-week project, which was 4 weeks for a reason. The loading of the soil and of the footings here had to be done at a minimum of 1 metre per week. This was stipulated because of the pore fluid pressures within the ground at the base, and we didn't want to create any slip failures along the base that would ultimately cause a failure in the bund. A key trench was dug along the bottom into the Charmouth mudstone, and that was ramaxed in with a roller, sheep's foot roller, and that was built up to avoid any water going either around the head wall that we see here, under the bund, or creating failure planes within the rock, within the mudstone. This went on, and in accordance with the CIRIA document, which is maximum of 1 metre loading per week, so we'd have to do it over about 3 days, and then come back next week and do another 3 days. Meanwhile, the plant was used somewhere else on site. Step trenches were used along the bottom of the key trench, and the reason why we had the key trench is, you can't really make it out on here, but you do have zones of silty material, sandy horizons within the Charmouth mudstone that could act as a route for water to pass out of the bund. The head wall here was throttled, and the calculations that we had done based on the surface area, the development area, meant that we kind of had to be a bit of a hydrogeologist at one point. We had to be a bit of a geotechnical engineer at one point. We had worked with a few civils guys to work out the best route of how to make this in line with the CIRIA guidance document. And then we also had the problem with the contaminated land as well, and that was heavy metals from a previous army use. Building this was pretty much it was very quick. And so we had to have real-time testing to prove that what we were doing was in accordance with the documentation. This is a technician with a nuclear density gauge, and that proves the amount of air voids that we find within the compacted mudstone, which is taken from the borrow pit beyond that Land Rover. That meant that we could do real-time analysis of if the compaction to the CIRIA guide and the level between the layers was adequate to reduce the creation of slip planes and failure areas of weakness within the bund. We also took out core cutters, and you can see some holes for the shear vanes there where we had taken stuff to go back to the lab on a quick turnaround to get data back the next day to prove and calibrate from what we got from the NDM with a more accurate lab test. The results were in from the testing because we also compared testing that we had done throughout with a more long-term lab testing schedule. So we have, if I can read some of these off, we have Triaxial Tests, you have moisture content values, PIDs, all for the clay. So we had to collate this data, compare it back to what we had said in our specification, and organise it and work out if we had passed or failed. We did have a few failures on the angle of friction. Now, the angle of friction was decided that it had to be 25 degrees, that's our phi angle, for the internal friction of the strength of the clay. We had failures in all of these, and I'll talk a bit after why they failed. But we managed to remodel the slope with the new data. We fed it back into the original model we had, and with the geotechnical engineers we worked with on this, and we worked out that due to the cohesive nature and the really high cohesion values, we were able to justify that the slope and the bund were still competent. A lot of this came down to, was it a homogeneous material to begin with? We hoped it would have been, but as with all things geology, it's never quite as you hope. And ultimately, we signed it off and said it was good enough. The reason why the phi angles failed is because we took kind of a dictionary, a lookup chart, rather than doing our original testing in the first place. The shear testing that we did was on a very short time scale, rather than the long-term 100-year life of the bund that we were expecting. Got a few before and after photos, so these are all in the same direction. That's with the Charmouth mudstone before it's been levelled and graded, and then that was it on Tuesday with a nice bit of grass on it. And that's the stream that goes in to feed into the bund. and that was it during its creation with the head wall, the ram axe, and the dumper truck. So Geologist, a jack of all trades, yes. Seen the most rocks, yes. I think they're both equally relevant. So we buried the contaminated land in the borrow pit and capped it off in line with the remedial method statement approved by the EHO. We modelled it and we remodeled it with the assumptions and changed our original plan based on more data. We did a resource evaluation. We used geotechnical design and testing, and the homogeneous material and the pragmatic analysis of testing meant that we could look back at the data, analyze it in lieu of all the other data, and eventually agree that what we had built was competent. Question time.